Hello, my name is Li Yi. I am the overseas sales of Jiuhao Micro-electronics. Jiuhao Micro-electronics is a fabless semiconductor design company. Our business is mostly on ASICs for sensor signal conditioners. ASICs is application-specific integrated circuits, and sensor signal conditioners are usually called SSC. So in this video, I will use SSC to mean the sensor signal conditioners. This video, I will introduce how to calibrate our SSC JHM1101 to a current transducer. 4 to 20 milliamperes current transducer. JHM1101 is designed for differential resistive bridge sensor signals or differential Wheatstone bridge sensor signals. Here on the screen, we are now seeing the block diagram of JHM1101. The JHM1101 functions are shown inside the block. Here, to the left, outside of the block, we can see a gray area. This is the electrical circuit for a differential Wheatstone bridge, and here we can see it is marked sensor. The sensor signals are generated by this differential Wheatstone bridge circuit. In this video, I will call this current for sensor signals, or the sensing elements, the sensor. And here on this screen, we can see some final applicational products. They are also marked sensors in this picture. So, to avoid confusion of concepts, I will call these final products transducers. So in this video, the current for sensor signals, here, this part, are called sensor, and the final products are called transducer. Okay, next. The calibration steps are complicated, and here is a flow chart of the calibration process. Okay, we can see we use it to make all the steps clear. The flow chart is included in the calibration menu. This video will also follow the flow chart step by step to make the video clear. Okay, so let's begin on the first step, the preparation. Here, the first, we need to prepare a GMCB calibration board. In this video, we will introduce how to use this calibration board. We will use a JHM1101 transducer simulating board. To make the video simple, we use the simulating board to simulate a current transducer. We can provide a 0-point signal and a full point signal by using the jumps on the simulating board. User can use a real transducer, like a pressure transducer, and give real sensor signals to make the calibration. For the JHM1101 current transducer, we need 5 wires. We will introduce the wire connections between the transducer and the calibration board on later video. And you see here on the hardware connection steps. We'll show it on later video. Also, we will need a calibration manual, of course. And finally, we need an ampere meter, or sometimes called a current meter. A calibration board can measure the output current and show the measured current value on the software. But we can also use the ampere meter to view the reading in a different way. We will see the deviation between the ampere meter and on the software are very, very small, but usually. Okay, let's see the real stuffs for the calibration. Let's begin. This video is to use the calibration board to calibrate the sensor signal conditioner JHM1101 to a current transducer, a 4 to 20 milliamperes current transducer. This is our task. Before the calibration, I'm now showing what we have prepared for this operation. Here is the key instrument, the GMCB calibration board we are going to use. Here in this area, we can see the model name GMCB printed on the board. The software are already installed on the computer. And this is a signal wire which connects to the calibration board and the RS485 USB wire. We will introduce how to connect these two wires on later steps. On this calibration board, we need two power supplies. One is 12 volts and one is 12 volts. Please pay attention here. The voltage 24 volts and 12 volts are printed here. And for the transducer, the current transducer, for the current transducer, 5 wires are required for the JHM1101 current transducer. User can use a true current transducer. For real transducer, you need to supply true pressures for 0 point and for full points. Here, to make the video simple, we are using a simulating board for the current transducer. I will introduce how to connect the 5 wires with the GMCB calibration board in later steps. The function of the simulating board is very simple. To simulate a 0-point signal and a full-point signal, we need only to change the jumpers. Finally, we need an ampere meter. The calibration board has the function to measure the outputs. The outputs can be shown on the software, but we can use the ampere meter to connect with the output and to view the reading on the ampere meter. Now we make an overview. There's 2 power supplies. This is RS485 USB wire. This is the signal wire connects between the calibration board and the RS485 wire. This is the GMCB calibration board. This is our simulating board to simulate a current transducer. All these materials we need are listed on the flow chart. Please pay attention on the listed here. In later video, we will show the operations step by step. All the information we show on this video are also included in the operation manual. This video is to be used with the operation manual together. Okay, we are now here. I just saw the video. The information printed on the PCB is not very clear, so we are seeing the photos of this calibration board again. Here, we can see the model's name printed here, GMCB 3.1. The initial letter G is hidden, and above it, there is the black one. This is a connector for the signal wire. This is a non-reversible socket or an error-proof socket. The signal wire will be plugged into this socket and it can't be reversed. Here, we see here, a green connector. There are 4 pins and they are for the power suppliers. We can see here the words that are printed next to it, 24 volts and 12 volts. The board needs 2 power suppliers. One is for 24 volts and another one is for 12 volts. Okay, we see another photo. We can see the printed information better. This Jiuhao Micro is our company's name. GMCB is the board's name, and 3.1 is the version of the board. And here, this green connector is for power supply. This 24 volts and this is 12 volts for 2 power suppliers. Okay, way back to the original photo. So at the end of this PCB, we can see a border extender connector, the border extender connector. The specification of this connector is 32 plus 3. 32 is here, 1, 2, 3, and 32. And each of the row, there are 3 pins. And for the first row, the name of the pins are A1, D1, and G1. For the last of the row, the name of the pins are A32, D32, and G32. Okay. Okay, that's the photos. Okay, we are now beginning the hardware connection. The first step is to connect the simulating transducer with the calibration board. Here is the specification of the connector, which is 32 plus 3. We can see this one printed here, 1 and 32. And we can see that each row there are 3 pins. There are 3 pins for each row. And here, the name of the first row is A1, D1, G1. The name of the last row is A32, D32, and G32. On the operation menu, we can see photos more clearly. So now we are going to see the big screen for the connection. A JHM1101 current transducer requires 5 wires. Look at this big screen. This is the 32 plus 3 connector. We will use the first row and the 17th row for the 5 wires of the current transducer. These two pins A1 and G1 are for the positive and the negative voltages. D1 is for the SO pin, the one-wire interface. And SO is the one-wire interface for communication and for signals. And this is A17 for VPP, for OTP writing. The OTP writing requires high voltages, requires 77.5 volts to make the burning or the writing. And so this is the VPP, and this G17 is the ground. So this is the connection. We are now making the connections between the stimulating current transducer and the calibration board. Connection. We are using 2 rows, row 1 and row 17. Okay, we have just finished the connections between the stimulating current transducer with the calibration board. Next step, we will make connections between the signal wire and the RS485 wire. This signal wire will be connected to the calibration board. Here is the socket. It's a non-reversible plug, so we can just plug it in. And here, please zoom it. This is A, B, and G. Here, for the RS485 wire, on the operation manual, we will also mark A, B, and G. We just connect the wires together. This is the connection between the signal wire and the RS485 wire. The connection is very simple. We just need to pay attention to the indications here with the RS485. The indications are shown on the menu. And then we will plug this is the USB plug, and we just connect to the host. Okay, this is the operation manual. We can see this calibration board is connected, communicate with the host computer through a signal wire connected with an RS485 wire. Here on the board, you can see this black one is the connector. It's a non-reversible connector, error-proof connector, so you can't make reverse of the connection. And the signal wire is 3 lines, and here on the menu you can see the RS485. They are connected here, A, B, and ground. And also we have the indications here, just next to the socket. We see this is B, A, and G. We just make the 3 lines end to end connected, so the connection will be finished. It's very simple. Okay, We are on the power connection step. The green connector is for power connection. Please zoom in to make it clear. We can see the indicators 24V and 12V. So the board requires two power supplies, 24 volts and 12 volts. The other two are for ground. Here we can see we are using two power suppliers. Please see the displays here, 24 and 12 volt. So here we need to pay attention. When the two voltages are from two different equipment, the two ground terminals should be connected together for common ground. Now is the operation. Here, this connector is to make the connection simple and easier. The two power suppliers are connected. So now, this is connecting the power supply. And now she is using a wire to connect the grounds, both grounds. Here, to connect both grounds to make the common ground. Okay. The boarder can measure the voltages, currents, and display the measured values on the host computer. But we can also use an external multimeter for the measurement. For current transducer, the multimeter can be series connected to the boarder. Okay, we are now connected. The multimeter is connected to the boarder in series. Okay, this is the connection in series. We are now using the calibration software. This software has been already installed on the computer. Double-click the software. It starts up and is trying to connect the calibration board automatically. This button is blue. It means that the connection is not successful. We are now turning on the two powers, and then click the button again. Now it's connecting, and the color of the button changed to green. It means the boarder connection is successful. We can see on the screen the button is green and showed connected. The connection is succeed. We will view the flow chart again. Okay, this is the flow chart, and we have started the software. And the step of communications connection is finished. Next step is to scan the GMCB calibration board. Here we see the manual device, and below it is scan board. We connect it. When the board scan complete, we can see the message GMCB is the board number, V3.0 is the version, 007 is the ID of the board. Totally 16 calibration borders can be cascaded together. 240603 is the firm burning date of the board. We have finished the scan calibration board, and we will do the initial setting for the board. This board can support different transducer types. In this video, we will choose the current output 4 to 20 milliamperes. We will choose in 1 temperature, 2 points calibration, and setting the value to 4 to 20 milliamperes. Also, we will choose retest. So I will make the operation. We see the menu setting, and then the configuration. Here, the values will be set later. First, we need to choose the current transducer type. This is the transducer type for first is proportional voltage output for wires. Then is absolute voltage output for wires. In this video, we will use 4 to 20 milliamperes current output 5 wires. We have also other types. These messages are in Chinese and we will correct them to English later. Then we will choose the algorithm selection. We choose 2 points in 1 temperature, and we set 4 milliamperes for 0 point and 20 milliamperes for full point. Our JHM1101 designs for several algorithm methods. So we can see maximum 5 points and 3 temperatures. This video, we will use this 1 temperature 2 point calibration, and I'll save it. We can see here the button displays different options. The button will be different. I'll go back to show the different algorithm method. Okay. So the setting and the configuration. So I will choose, we can choose 4 point. Pay attention, when I choose 4 point, on the coordinate graph, there are 4 points. 2 points in 25 degrees and 2 points in 85 degrees. This temperature can also change, and we set the values to 4 milliamperes, 20 milliamperes, and below are the same. We choose the different algorithm method, and the buttons on the right will be changed accordingly. So some value will disappear or agree, and you can't operate it. To make the video simple, we'll still use 2 point in 1 temperature. So we can see the values are not changed automatically. We will set it manually. We will set the first one in 4 and then in 20. We need to pay attention to it. So if we don't set this, forget to do this, there will be errors for the algorithm. Okay, so the orders in the up block will be set later, and I will press save. And then this is the buttons related to the setting. Here we can see there are 2 retest. So I will show it. The retest is the setting here. There are 2 buttons. The options are retest on the first temperature. If we don't choose it, the 2 buttons will be disappeared or be gray, and we can't operate it. Reset button. And in this video, we choose the first temperature area, and we need to do the retest. We save, and so there are 4 buttons can be operated, and so this is the setting. We have just finished the step initial setting for the calibration board, and the next step is the JHM1101 chip scan. We see the procedure. So I emphasize that we are using the OTP and all the calibration data was stored on the host computer. So we need an ID to make the relationship. So we will scan if the chip ID was written. If it's not written, we will write it. And if it's already written, we will do the next step, out setting. So here is the operation. Here is the operation. We see the menu board. Okay, we scan. Okay, it's we see. Here I will use a new I will use a chip that already be written, and then I will show it. This I just change the chip to another one, so I need to do the initialize. And here, after the initialize, there's all the empty for the sensor ID and the status. I will scan. So it's I will scan. Okay. So after we change the chip, we need to do the initialization. When we change the chip on the process, we need to do the initialization. And after doing it, and then I will scan. You see, they are empty, and I scan it. We can see this ID already be written, and the status is ID. So now I changed the new ID, not written. The ID is not written, and I do the initiate, and then I scan. You can see here the status ID unwritten, and there is no sensor ID. And then I write the ID. Okay, I will do the operation write ID. I write it, and pay attention. If you write it, you can't write it again. So now the sensor ID is here, and the status is that ID written. If we write the ID, we can't change it anymore. So so we will do the next steps. Okay, we have finished the chip ID writing. When the ID was written, we go to the next step, outset. We will set the gain, polarity, and offset. I will show the operation. Okay, here we find the menu setting, and the first one is configuration. It's for the calibration board. We are using the auto configuration. It's used for the sensor ID. We can see the sensor ID is here, and we need the finish the ID writing. Without the ID, the operation can't be executed, and we need to do the auto configuration step by step. First, we need to back to the hardware. Okay, let's see. Here we can see here we are using a simulating transducer board. We use a jumper to generate a 0-point signal. So we already this jumper has cap of the jumper has been changed, and we back to the software. I click the software auto configuration. I clicked the button 0-point collection. Here we can see the row for. Okay, we back to the hardware simulating board again. I change the cap and then to generate a full point signal, and I collect the full point collection. Okay, I collect it. We can see the message on the screen. Finished. We got the full point signals, and at this time the gain, polarity, and offset are empty. I clicked the calculation, and there is the gain, polarity, and offset. So at this step, now we have finished the auto configuration, and I will save it. Okay, we save it to the next step. Okay, we began the step for data collection. Here we can see collect the points. This is the flow chart. We getting 0 point and full point values. Before the operation, we need to change the transducer signals. We back to the hardware, the simulating transducer board. The simulating transducer is on 0 point signal now. We back to the software. We are collecting the 0 point value. Pay attention, the buttons are double-clicked. You can see the row data on the column of the table. Okay, the data here on the column of the table. We go back to the hardware. We change, okay, we go back to the hardware. We change the jumper cap of the jumper on the board. The simulating transducer is on full point signal now. Then we double click the button for full point value collection. It collected the full point value and the full point retesting value at the same time. Please remember the calibration board configuration on former step. Retesting is selected for the better accuracy. So we can't calculate it now. We need to collect the 0 point retesting value before the calculation. The full point retesting value is already collected at the same time before. So we go back to the hardware. We change the jumper and generated 0 point value from the simulating board. Okay, we change the jumper and then generated 0 point value. Okay, I double clicked the button to collect the retest value for the 0 point. Then, okay, I calculate. Please pay attention to the table. Here, the status is calculation passed in green color, and we can see the 0 point. It's very close to 4 milliamperes, and we can see it's also full point value. It's also very close. So we have finished the calibration. Okay, we have finished the data collection and the data retesting collection, and now we also finished the calculation. This is the calculation for the 1101 internal calculation. We need to make a 0 point error test and a full point error test before writing the OTP. So we back to the hardware. The simulating transducer board, here we set it to on full point. If you are using a true transducer, please let it work on full point. We back to the software. We click the error test button. So we click it and we can see the screen. It goes to the error test display. So here we can see the expected value 4 milliamperes and 20 milliamperes. Please pay attention. The expected value should be in constant with the true transducer signals. This simulating transducer is in full position, so we need to select 20 milliamperes, and then we click error test. Okay, see 20 milliamperes for full position error test. Here we can see the sensor ID. This is the our expected value is 20 milliamperes, and the real test result is 19.993 milliamperes. So for this position is passed. The deviation is 0.04%. It's passed. So now I will do the zero error test. Before the test, we also need to change the hardware. The transducer signal should be changed to the 0 point, and I clicked the error test again. We can see here, there's sensor ID. The expected is 4 milliamperes, and the tested value is 4.001 milliamperes. Deviation small. The error test result is passed. So we do full point and 0 point test, and the order can be set by yourself. Okay, later is for OTP writing. We see the flow chart. We have performed both 0 point and 4 point error tests. Both tests are passed. The deviations are small. The next step is write to OTP. Writing OTP is very simple. Before it, I will make an explanation. Here on the left is the operation log. The log for every operation will be recorded and shown here. We need to check the log when the operation. I now click the button Write OTP. Click the button. It asked, do you confirm to write OTP? I clicked Confirmed. It showed OTP passed. 1101 has only one OTP, so you can only write it once. You can't change it anymore after writing the OTP. Okay. So, after the OTP writing, does it mean all steps has been finished? In fact, we need to verify the final results again. Here is the last test button. The last test is to verify if the real values meet the requirement. So in the hardware, the simulating transducer is providing a 0 point signal. I click the button, the display changed, and I click the last test again. So here is the value for 0 point. The expected value is 4 milliamperes. The real value is 4.008 milliamperes. The result is passed. So I change the simulating transducer to full point signal again. I change it to full point signal. And here I change the expected value to 20 milliamperes. For the former 0 point test, the expected value was already 4 milliamperes. I click last test button. So here on the display, we can see we got the expected value is 20 milliamperes. The real value is 19.909 milliamperes. The deviation is small. So we will see the ampere meters display in serial connection. Okay, we can see the ampere meters display. It's 20 milliamperes. For the full point value, we can compare the ampere meter. The value is constant with the software display value. Okay, now the simulating transducer will provide a 0 point value. 0 point. On the software, I change the expected value to 4 milliamperes. I test it. The software displays the value is 4.001. We can see the value on the amperes meter. It's 4.00 now. It's changing Now it's changing to 4.002. Okay, so to this step, we can say that the calibration is finished. The result is successful. The video is finished now.